So this lesson we're going to look at, re-look at definite integrals. We've touched upon this already. We're going to go through I'll go through the starter if you need. You may have hopefully already tried both these questions. So this was something called finding derivatives from first principles. So if we're going to find f prime of x, given that this is our f of x, we will use the formula above. So it's the limit as h tends towards 0. Now I've got a function of x, it's 2x squared plus 3. First thing this tells me is to substitute in x plus h into my function. So where it says x, I'm going to write x plus h. Then I need to subtract my function, my f of x. So I'm going to subtract all of that. I've put in some brackets to make sure I don't make that common mistake when you're subtracting, and that's all over h. So I think we need to do a bit of expanding, a bit of tidying up, and hopefully a lot of this will cancel out. So I've got x squared 2, lots of x squared. Guys, if you want to take an extra line, or if you want to do expanding this on the side, that's absolutely fine. I'd have 4xh here, then 2h squared plus 3, and I'll expand this as well. Okay, and we'll see that I've got 2x squared minus 2x squared. Let's get rid of those. I also have plus 3 minus 3, they can go. And then I've got 3 terms left, and they all have a common factor of h. So let's cancel out h from all of them. Okay, as we said before, a lot of those terms have disappeared or become simpler. So we're left with this. As h goes to 0, 4x plus 2h. So what does that mean? It means as h tends towards 0, we're going to get towards this gradient function. And as h tends towards 0, this whole term will tend towards 0. And so what will happen is that we will be left with 4x. And thinking about it, we know that if we differentiate our function, we would get 4x. So that follows. A little bit of algebra practice. The second question, we were doing quite a lot of this near the start of the unit. We're after an expression for this area. We'd say that the area is the integral from 1 to 3 of x squared plus 1 with respect to x. And we could use our calculators. We've got that useful button in the toolbox here to evaluate it. X squared plus 1, and then we just put in an x here. There we go. So that is 10 2/3. So far, hopefully not too much to worry about. We're going to look a little bit more at area now this lesson. So we have been looking at finding areas using our calculator. We can also use our learning about antiderivatives as well. So if we have an area under a curve and we're going from a to x, we're saying this is this area here. If we have a small value of h, the area of a of x plus h would be approximately the area of a that we had before plus the area of the rectangle below the curve between x and x plus h. So it means it's approximately equal to this. This is our width of our rectangle h, and the height is given from our function, the y-coordinate of our function if you like. And obviously as h tends to 0, as this becomes more narrow, the result will get more accurate. And we looked at that idea earlier in the unit with making the rectangles increasingly narrow, because it means that they more closely approximate the shape of the curve. So if we take this result, it can be rearranged in this form. If you want to pause, just verify that it rearranges. You can of course do that. And as h moves towards 0, as these rectangles get thinner and thinner, we can say that f of x is equal to the limit of this, which I hope we recognise from this very first question. Okay, so that tells us then that f of x is equal to dA by dx, where A was the area. And that tells us that A is equal to the integral of f of x. Oops, hang on, there we go. So if f of x is equal to this derivative, the area is equal to the integral. And you'll remember we sometimes use capital F to represent when we've integrated function little f. And of course, we have this plus c. We'll go on to see that this plus c doesn't really make much of a difference with definite integrals. Okay, so let's just do a little bit of reading. The plus c term of the indefinite integral just reflects the arbitrary choices of where the area was measured from. As indicated in the examples below, this choice does not affect the calculation of the definite integral. We will find that the plus c does not have an effect on finding the area. So, if we take a look at finding the area between our curve, x squared plus 1, the x-axis, and the vertical lines 2 and 3. If you remember, we were looking at this function a little bit earlier. So, using the same notation as we had, we've got our function, and we're going to call capital F the antiderivative. So, if we want to find the antiderivative, we're going to have to integrate x squared plus 1 with respect to x. So, we know that we can integrate these kind of functions, increase the power by 1 and divide by the new power. And of course we'll get a plus c. So if we want to find this area from 2 to 3, what we're going to have to find then is, so the required area is that we want to find f of 3, so the area all the way up to 3, minus f of 2. So we're going to find all this area all the way up here, and then we'll subtract this area away, and we'll be left with the area from 2 to 3. Okay, so to do that, we now know we've got function f, big capital F, so we need to substitute 3 into that first of all. A third times 3 cubed plus 3 plus c, and we're going to subtract capital F of 2. A third times 2 cubed plus 2 plus c. One thing you'll notice is that c minus the c will cancel, and that will always happen. Okay, so that plus c is less important with definite integrals. Okay, so we would get 12, I've already cancelled the c's out, and we'd get 14 thirds, which is 22 thirds. So this area here, the integral from 2 to 3, is worth 22 thirds. And what we've just used here is called the fundamental theorem of calculus. So if we want to find an area from A to B, or if we're going to find a definite integral from A to B, we do that by using the antiderivative. We do f of b minus f of a. This gives us a new way of calculating areas under the curve without needing to use the trapezium method, which was one of the approximation methods, or without using our GDC. Obviously, in our course, we will be using our calculator more often, but it's important that we are able to do this. So let's just wait for the page to turn. Let's have a look at a quick example of this. So if we want to find this area, what we're going to do is we're going to find the integral from 1 to 4 of this function. I'm going to rewrite this. Instead of being a fraction and a square root, let's make it in index form with respect to x. Now, this was just a question where you were allowed to use your calculator. The quickest method, the most efficient, would be to go and use this on our calculator. But we need to be able to do this without a calculator, and let's have a look at practicing these new skills. So, step 1, let's integrate. I'm going to increase the power by 1, divide by the new power, and the same again. That becomes a half. 2 divided by a half is 4. Right, new bit of notation for you. When we're doing a definite integral, when we have boundaries here, when we're looking over an interval, once we have integrated, we use square brackets. And what these are basically saying is we have integrated, we now need to substitute in these upper and lower boundaries. So it's an important step in your notation. Obviously, we should be integrating a whole function at once. It's often a bad habit that students get into of integrating the easy parts of the function first and then figuring out the more challenging parts later. If you need to do some work at the side to figure out a more challenging integral, do that, but integrate everything at once so it can all go from this notation to our square brackets and then on from there onto substituting. So now I'll substitute in my upper limit first. 4 cubed plus 4 times root 4 plus c, and I'm going to subtract, we always subtract, the lower limit. And of course, just as before, the c's will cancel out. Okay, they are definitely less important in definite integrals. There we go, 67 is our area, and of course you could check that using your calculator. I'll post solution for example 2.